in this session we are going to see one of the functionality of transport layer, which is congestion control. So transport layer can handle the congestion in two phases. One is slow start phase and another one is additive increase and multiplicative decrease phases, or else you can say that two algorithms, or else we can say that three phases. Okay, so what is the point we can write here is transport layer can handle congestion in the following three phases. They are, first one, slow start phase, second one, additive increase phase, and the third one, multiplicative decrease phase. Right. So regarding this slow start phase, additive increase phase and multiplicative decrease phase, now we are going to see some theory description. Okay. Right. So first we are going to see slow start phase. So what is the point we can write here is, initially the sender calculates the congestion window to the receiver with the size of one segment. So initially the sender calculates the congestion window to the receiver with the size of one segment. Next, coming to the second point. After transmission of one segment, the congestion window size becomes two. Next, after transmission of two segments, the congestion window size becomes 4. Next, coming to fourth point, after transmission of 4 segments, the congestion window size becomes 8. So here if you look at this, so initially it is 1, after transmission of 1 segment it becomes 2, after transmission of 2 segments it becomes 4, after transmission of 4 segments it becomes 8. So it means that if you observe these 4 points, we can easily conclude that there is an exponential growth in the congestion window size. So that is what my fifth point. So it seems that there is an exponential growth in the size of congestion window. Okay, so there is an exponential growth in the congestion window size. So this exponential growth is continued. So till what it is continued? So this exponential growth is continued this exponential growth in congestion window, okay. So this exponential growth in congestion window is continued till reaching the congestion threshold. So this exponential growth in the congestion window is continued till reaching the congestion threshold. Right. So now we are going to see additive increase phase. So what is this additive increase? First point here is, once the exponential growth, or else once the congestion window size is reached, the congestion threshold is reached, once the congestion window size is reached to the congestion threshold, okay. So once the congestion window size is reached to the congestion threshold, then from that moment onwards, there is a linear growth in the congestion window size. There is a linear growth in the congestion window size. There is a linear growth in the congestion window size. Next. So this linear growth in congestion window size is continued. This linear growth in the congestion window size is continued till timeout occurs. Right. So then we can have multiplicative decrease phase. Multiplicative decrease phase. Right. So what is the first point here is, when the timeout is occurred, when timeout occurs, then the congestion threshold for the next round of slow start must be set to half of the congestion window size, comma, and at the same time the congestion window size drops to drops to 1. So this is what multiplicative decrease phase. So here you can say that where is that congestion occurrence and where is that congestion avoidance and detection. So additive increase phase we are using for congestion avoidance, and multiplicative decrease we are using for congestion detection. Okay. So this is the way how TCP is handling the congestion in 3 phases. That is, first one is slow start phase, another one is additive increase phase, and another one is multiplicative decrease phase. Okay, so let's represent this theory part in a diagram, a simple diagram. Right. So if you consider this is a sender and it is a receiver, initially the sender is calculating a congestion window with a size of 1 segment. After transmission of this 1 segment, the congestion window size becomes 2. After transmission of 1 segment, the congestion window size becomes 2. Now we can transfer 2 segments. So first segment and its acknowledgement, second segment and its acknowledgement. So after transmission of 2 segments, the congestion window size becomes 4. After transmission of 2 segments, the congestion window size becomes 4. Now we have 4 segments here. So we have transferred first segment, we have transferred second segment, we have transferred the third segment, and we have also transferred the fourth segment. So after transmission of 4 segments, the congestion window size becomes 8. So if we assume that the congestion threshold is set to 8, let's assume that we are saying that the congestion threshold is 8. So once the congestion threshold is 8, so here we have reached congestion threshold. Now how many segments I can transfer? 8 segments. So we are transferring 8 segments here. 1, 2, 3, 4, 5, 6, 7 and 8. So total 8 segments we have transferred. So since 8 segments have transferred, it should be 16, but since it is congestion threshold, we can have a linear growth here, which is 9. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. So here it is 8 and here it is 9. So this is the congestion threshold. So till this point, we can say that this is slow start phase. Here we have started with additive increase phase. So this is the way how it goes. So this is what explanation for all these given points with respect to each phase. Okay. So now total this scenario we are going to express in a plot. Okay. So if we understand that plot, then it is easy to solve the numericals based on this TCP congestion control. Okay. Right. So now we are going to draw a plot here. Right. So to understand in a better way about this particular congestion control, we are considering some initial values, like congestion threshold value is given as 16 and the timeout is occurring at every 6th round. So these are the initial values which we are considering. Now we are giving a plot. So on x-axis we are considering number of rounds, and on y-axis we are considering congestion window size. Right. So initially we are saying that the congestion window size is 1. So initially, in the sense, in 0th round it is 1. In first round, so it means that in first round how many segments you have transferred? 2. We have transferred 2 segments here. And in second round, by the end of second round, what is the congestion window size we are getting? 4. By the end of third round, what is the congestion window size we are getting? 8. By the end of fourth round, what is the congestion window size we are getting? 16. So now congestion threshold is reached. So it means that from this point to till 16, this is called slow start phase. So this particular phase is called slow start phase. Now fifth round, so by congestion threshold, but timeout is occurring sixth round. So it means that till sixth round we should have linear increment. So that's why in fifth round it becomes 9 17. So in fifth round the congestion size becomes 17. In sixth round the congestion size becomes 18 because it is linear growth. So till this point, this is called additive increase phase. So now the timeout is occurring every sixth round. So whenever the timeout is occurring, then what we have to do? We have to calculate the congestion threshold for the next round of slow start, which is set to half of the congestion window. By sixth round, the congestion window size is 18, so that 18 by 2, which is 9. So after calculating the congestion threshold, in the same round, the congestion window size drops to initial size. In the same round, the congestion window size drops to initial size. Right. So now this is called multiplicative decrease phase. And I can say that this is the 0th round because in 0th round it is 1, so that in 6th round it is 1. Now 7th round I can consider as first round. In first round the congestion window size is 2. So in first round the congestion window size is 2. So 8th round I can consider as a second round, which is 4. And 9th round I can consider as a third round, which is 8. And 10th round I can consider as a fourth round, but it is 16. But the congestion threshold for the next round of slow start is 9. So it means that from this point to till 8, this is called slow start phase. This is called slow start phase. Then in 11th round, the congestion window size is, so in 10th round, the congestion window size is 9. In 11th round, the congestion window size is 10. In 12th round, the congestion size is 11. So, from this point to this point, this phase is called additive increase phase. Now, 12th round, this is the second round of 6th round. So, it means that here, again the congestion threshold for the next round of slow start, we need to calculate as it is the second round of 6th round at which the timeout is occurring. So, congestion threshold for the third round of slow start is, so by this 12th round the congestion size is 11, so that 11 by 2 which is 5.5. So, we can say either 5 or 6. So, after calculation of the congestion threshold, this should be drops to initial size. So, this should be drops to initial size. So, what is the initial size? 1. So, this is what multiplicative decrease phase. So, now this is my first round again. This is my initial round which is 0. Then first round is 13th round in which the congestion size can be 2. 14th I can consider as second round in which the congestion size is 4. 15th I can consider as third round in which the congestion size is 8, but it is crossing the congestion threshold. So, it means that from this point to this point, this is called slow start phase. So, in 15th round the congestion size becomes 5. So, in 15th round the congestion size becomes 5. In 16th round the congestion size becomes 6. In 17th round the congestion size becomes 7. In 18th round the congestion size becomes 8. So, it means that from this point to this point we can say that this is called additive increase phase. And here 18th round is the third round of 6th round at which the timeout is occurring. So, it means that, so whenever there is a timeout is occurred, then the congestion threshold for the next round of slow start we need to calculate. Now, it is 8 by 2 which is 4. So, after calculation of the congestion threshold, then it drops to initial size. Okay. So, this is what my multiplicative decrease phase. So, this way again we can have slow start phase. So, this way it continues. So, this is what the plot which is very helpful to us to understand how TCP is handling the congestion control using slow start phase and additive increase phases. So, here initially the congestion threshold is 16. So, here this is the point of congestion threshold. So, this is what first round of slow start. Additive increase and multiplicative decrease phases. And from this point onwards till this one, this is second round of slow start. Second round of slow start, additive increase and multiplicative decrease phases. So, in this second round of slow start or additive increase and multiplicative decrease phases, the congestion threshold is 8. Now, this is the third round of slow start phase. So, from here to here, this is third round of slow start and additive increase and multiplicative decrease phases in which the congestion threshold is 4. So, if you look at here, the congestion threshold is 16, here 8, then it is 4. So, this way it drops. So, this way it goes on drops. So, at some point of time the congestion threshold becomes 0, where at that point we can stop the slow start and additive increase phases, so additive increase and multiplicative decrease phases. So, this is the way how congestion control can be handled by transport layer in these three phases, which is slow start phase, and additive increase phase, and multiplicative decrease phases. Okay. So I hope you are clear with my explanation. Thank you. In this session, we are going to see how to calculate wraparound time, and which is very important numerical as part of our transport layer. We have already previous gate questions based on this particular wraparound time calculation. So first let's understand what do you mean by wraparound. So see, for example, if it is by sliding window, I mean this is my sender sliding window and it is my receiver sliding window. So these are the frame sequence numbers I have 0, 1, 2, 3, 0, 1, 2, 3 and so on. Similarly on receiver side also I am having frame sequence numbers like 0, 1, 2, 3, 0, 1, 2, 3 and so on. So here after 0, 1, 2, 3 I am unable to find 4, 5, 6, 7, 8, 9 and etc. So why I am unable to find? The reason is I have used 2 bits to represent the frame sequence number. So if it is a frame sequence number, then this can be represented as 0, 0, 0, 1, 1, 0 and 1, 1. So it means that we have used 2 bits to represent the frame sequence number, so that with 2-bit frame sequence number field we can have 4 frames. And those 4 frames having the sequence numbers which are ranging from frame 0 to frame 3. For example, if I have 12 number of frames, these 12 number of frames of message I am having, what is the how the sequence number can be generated for all these 12 number of frames with 2-bit frame sequence number field is this way. So first 4 will have these sequence numbers, and the next 4 also will have the same sequence numbers, and the next 4 also will have the same sequence numbers. So it means that this is one set of sequence number. After this set of sequence numbers, again we are generating the same set of sequence numbers, and after this set of sequence numbers again we are generating the same set of sequence numbers. So all these sequence numbers are said to be wraparound sequence numbers. These sequence numbers are said to be wraparound sequence numbers, and after generation of one set of sequence numbers, to generate the next set of sequence numbers, it takes some time, which is called wraparound time. So wraparound time is the time which is used to generate the same set of sequence numbers after generation of one set of frame sequence numbers. So already one set of sequence numbers are generated here. To generate the same set of sequence numbers, there is some time consuming. That time consuming is called wraparound time. So this is what the definition for wraparound time. And how can we calculate wraparound time here? So for that, let's consider a small numeric here. So the numeric statement is, in 40 Mbps line, how long approximately does it take a wraparound 32-bit sequence number? So the sequence number, how many number of bits we are using in the sequence number field? 32-bit. So with 32-bit frame sequence number, we can have 0 to 2 power 32 minus 1. These number of frame sequence numbers are possible with 32-bit frame sequence number field. After this, again we can have the same set of sequence numbers. After this, again we are having the same set of sequence numbers. This way it goes. Yes or no? So this is one set, this is one set, and this is another set. So now after generation of this set of sequence numbers with 32-bit frame sequence number field, to generate the same set of sequence numbers, how much time it takes? With 40 Mbps of bandwidth of the line. So this is what the question statement meaning. Okay? So with 32-bit frame sequence number field and by having the bandwidth of 40 Mbps, how much time it takes to generate the same set of sequence numbers? So that is what we are going to calculate here. Okay? Right. So first let's consider bandwidth. So what is the bandwidth it has given? 40 Mbps. So what does it mean is, within 1 second 40 megabits we can generate. So 40 megabits are generated. So within 1 second, 40 into 2 power 20 number of bits we are able to generate. Okay. Then I am converting these bits into bytes. So means that simply dividing this by 8 so that I can have 5. So 5 into 2 power 20 bytes of data we can generate within one sequence number, within 1 second. Okay, so within 1 second, these number of bytes we are able to transfer, 5 into 2 power 20 number of bytes. And you know that TCP is a byte oriented protocol. It is a byte oriented protocol. So what is the meaning of byte oriented here is allocating the sequence number to each and every byte. So if I am having 5 into 2 power 20 number of bytes, okay, so then how many number of sequence numbers that are available to me? Since you are allocating one sequence number for 1 byte, since I am having 5 into 2 power 20 number of bytes, I can say that I am having 5 into 2 power 20 number of sequence numbers. So within 1 second we are able to generate 5 into 2 power 20 number of sequence numbers. Are you clear with this point? So TCP is a byte oriented protocol. It means that it assigns a sequence number to each and every byte. I am having these number of bytes. For each byte, if one sequence number, then if I am having 5 into 2 power 20 number of bytes, then how many sequence numbers can be available there? 5 into 2 power 20. So within 1 second, 5 into 2 power 20 number of sequence numbers we are able to generate. But how many sequence numbers we need to generate? 0 to 2 to the power of 32 minus 1 means that 2 power 32 number of sequence numbers we need to generate. So to generate 2 power 32 number of sequence numbers, how much time it takes? This is what wraparound time. Clear? So then to generate 2 power 32 number of sequence numbers, so if within 1 second if you are able to generate 5 into 2 power 20 number of sequence numbers, within so to generate these 2 power 32 number of sequence numbers, how much time it takes? That is 2 power 32 by 5 into 2 power 20. So 2 power 20, 2 power 32 gets cancelled. So these number of seconds it requires to generate the 2 power 32 number of sequence numbers. Then it is 2 power 12. So 2 power 12 means 4096. So 2 power 10 is 1024. 2 power 11 is 2048, and 2 power 12 is 4096. So 4096 by 5 seconds it takes to generate 2 power 32 number of sequence numbers. So 4096, if I divide this by 5, 5 8s are 40, then 9, 5 1s are 819.2 seconds are required to generate 2 power 32 number of sequence numbers, but it is in seconds, but the options are in terms of minutes. 1 minute is equals to 60 seconds. Now this is seconds. So now if I want to convert this into minutes, then simply divide this 819.2 by 60. Then closely it can be, so by 60 if I do this, then it can be like almost we can have 14 minutes. 14 minutes closely is required to generate 2 power 32 number of sequence numbers. So after generation of these number of sequence number, to generate the same set of sequence numbers, it takes 14 minutes of time approximately for this scenario. So this is the way how can we calculate wraparound time in the case of TCP. Okay. So I hope you are clear with this explanation. Thank you.